All right, welcome back. Today we're going to take a look at simplifying radicals. From here on out, the expectation is going to be that the final form of any radical equation or expression, or any part of an equation or expression, must be simplified completely in order for you to receive full credit for your work. So today we're going to look at some strategies that are going to help you with that. We're also going to talk about conjugates, so that we can deal with radicals that are inside the denominator of a fraction. So the strategy that I like to use for this is a tree diagram. And I'll go ahead and draw this tree off the side so I don't run out of space on the bottom. But I'm going to look for two factor pairs of the number 20. And I'm going to look directly at these factor pairs in terms of perfect squares. So this is the only time I'm going to do this, but I want to show you what I mean by that. Two factor pairs of 20 are 1 and 20, 2 and 10, and 4 and 5. Of course, 5 and 4 is, but I know I've repeated, so this is my complete list. The two that are the best choice for this particular strategy is going to be the 4 and the 5, because 4 is a perfect square. So what I'm basically doing here is I'm saying that I'm going to take the number 20 and I'm going to break it apart into 4 times 5. What I'm going to do next is I'm going to say that, okay, if the square root of 4 times 5 is the same as the square root of 4 times the square root of 5, then I can simplify the square root of 4 to 2. And that's going to be 2 square roots of 5. So this is the process that we're going to use to help us simplify radicals. However, this is exactly the way I'm going to do it. I'm going to look for the factor pairs of 20, and I'm going to try to use the ones that are perfect squares. I'm going to go ahead and make an additional branch on the 4, and that's going to become 2 and 2. And see this pair right here? This pair comes out as a perfect square, so that's why this becomes a 2. But when you get good at this, you just recognize that the square root of 4 is 2, and that's why it comes out of the radical, like this. Let's practice it again with 18. So the two numbers I want to use are either going to be 6 and 3 or 9 and 2. I like 9 and 2 because 9 is a perfect square. That means the square root of 9 is 3, so it's negative 3, because that's already there, times the square root of 9, which is 3, times the square root of 2. 3 times 3 is 9, so the final answer here is negative 9 times the square root of 2. Let's look at it one more time with 48. Okay, 48, that's going to be 16 and 3, because 16 is 4 squared. So it's going to be 2/3, because 2/3 is already there. Please get in the habit of looking for that number. You'd be surprised at how many people leave that number off. The square root of 16 is 4, so that's times 4 times the square root of 3, the number that's left inside. So 2 times 4 is 8, so that means that this simplified is 8/3 times the square root of 3. Alright, now this can be accomplished with variables as well. No big deal, it's very easy. So we're going to use 48 again. I'm going to still get in the habit of writing my tree diagram, even though we just used 48 before. 16 is my perfect square, so it comes out. So that's going to be 4. Now what I do here is, to keep myself organized, I make a little space for all of my numbers and variables that will be on the outside, and then of course I put my radical here. The 3 stays inside, so I'm going to put that 3 right there. Now what I do here is I write out my x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now because this is a square root, I'm circling pairs of x's. So that means this pair comes out as 1, this pair comes out as 1, this pair, and this pair, and this pair. Now there are no x's left over, so that means it's going to be x to the 5th power on the outside, because a total of 1, 2, 3, 4, 5 pairs of x's would come out of the square root. I'm going to do the exact same thing with the y, so it's going to be y, y, and y. I'm going to circle my pair, and the reason I'm circling 2 of them, remember, is it's a square root, and the square root means 2, and so that's what I'm looking at in this particular case. So notice here I've circled 1 pair of y's, so that means 1 y comes out. There is still a y left over, just like the 3, so that means that there's a y that stays inside the radical as well. This is the simplified form of letter G. I'd like you to try B, D, and F on your own right now, please, before moving on, and we'll discuss those at the beginning of class tomorrow. All right, hopefully you've had a chance to go through those, so please, if you haven't, go back at the end of the video and take care of that. It's critical that we're practicing this on our own so that you can get an understanding of how to do this. All right, in question number 2 and question number 3, now we're going to be multiplying radicals. The way that I like to approach this is I like to multiply what's on the outside of the radicals together and what's on the inside of the radicals together. We can't really combine them together. They're like terms in that matter, but in this case I'm going to multiply 3 times 1, which is 3, and 10 times 5, which is 50. Remember, we've got to make sure that this can't be simplified before saying that this is our final answer. So remember, I'm looking for perfect squares, so I'm going to go with 25 and 2. The square root of 25 is 5, so it's 3, the number that's already out there, times 5 times the square root of 2. 3 times 5 is 15, so the final answer is 15 square roots of 2. Go ahead and try number 3 on your own before moving on. All right, the next thing we're going to take a look at here is dividing radicals. Dividing radicals is the next step, because down here below we're going to start talking about rationalizing the denominator. So we'll take a look at these 3 examples here for a second so you can see what it is we're supposed to do. If I have a radical over a fraction, that means I can rewrite it as 2 separate radicals over the numerator divided by the square root of 36. So the reason I want to do that is because now what I can do is I can take a look at each number individually, and in this case it works out that they're both perfect squares, so it's 5 divided by 6. So in this case the radical is already written this way, so I can go ahead and reverse it, and I can rewrite it as the square root of 27 divided by 3. And the reason I want to do that is because if I simplify this number, 27 divided by 3, I get the square root of 9, which is 3. And now this is the only case where I can't do that because the radical is clearly over the numerator only, not the numerator and the denominator. So instead what I've got to do is I've got to simplify 27, and I'm going to go ahead and turn it into 9 times 3. And the reason is because 9 is a perfect square, and the square root of 9 is 3. So that's 3 square roots of 3 divided by 3. I can cancel out the 3's, and the remaining answer is my simplified expression, the square root of 3. So those are 3 different places where you will be able to simplify radicals involving fractions or dividing them. Next thing we're going to talk about is rationalizing the denominator. And the rationalizing the denominator is actually an outdated strategy because the graphing calculators can do this now, but it is still something we want to teach because I'm the algebra teacher and that's what I do. I teach algebra. So the process of rationalizing the denominator is removing the radical from the denominator of a fraction. Before calculators were invented, this was an impossible thing to solve. So we had to move it out of the denominator, and the way that we would do that is by multiplying both the top and the bottom of the fraction by that radical that we wanted to get out. So we're going to multiply both the top and the bottom by the square root of 3. What that leaves me on the numerator is the square root of 3, and 3 times 3 is 9, so that's going to be the square root of 9. The square root of 9 is 3, so it becomes the square root of 3 over 3. Now over here, there is a slight variation here in that there is already a number in place. Now, in order to keep this in simplest terms, we just want to multiply the top and the bottom of the fraction by the radical. If you go ahead and multiply it by the entire denominator, nothing is going to change. It's just that you have to simplify at your last step. So we're keeping it in simplest terms by doing what I'm doing here. But if you do throw the 3 in, it's not a big deal. You just factor it out at the end. All right, so now I get 4 square roots of 30, because 6 times 5 is 30, divided by 3 times the square root of 25. I'm going to simplify, and and I get 4 square roots of 30 divided by 15. And I can't simplify 30 because if I break down 30, I get 6 and 5, and 6 becomes 2 and 3, but these numbers don't break down anymore because there's no pairs, so that means the square root of 30 is the simplest form of that particular radical. Now the reason we do this, well, I'm getting ahead of myself, sorry. Let's take a look at adding and subtracting radicals before I talk about conjugates. So in order to add and subtract radicals, we have to have like terms. Okay, so much like adding 5x plus 6x to make 11x, and likewise adding 5x plus 6y, I can't combine them because they're not like terms. That is the strategy we're going to use here when adding and subtracting radicals. So in order to have like terms, we have to have like radicands. Notice that in number 9, the radicands are the same, therefore we can add and subtract those together. Over here on the surface, 5 and 20 are different, so we can't add those together in their current state that they're in. We'll have to simplify 20. We'll get to that in a second. Okay, so just like this, the x remains an x. The square root of 2 is going to remain a square root of 2. So 5 minus 7 is negative 2 times the square root of 2. And that's your final simplified expression. So I'm going to go ahead and break 20 down to 4 and 5. 4 because it's a perfect square. I'm going to leave 3 square roots of 5 alone for just a second, and I'm going to add 2 square roots of 5 to that. Now I've got my like terms. Now I can add them. 3 plus 2 is 5. 5 square roots of 5 is my simplified expression. Conjugates. So we're going to use conjugates to help us in rationalizing the denominator in a couple of these problems. So I'm going to go ahead and go through 11, 12, and 13 and leave 14 and 15 for you to do on your own so you can get some practice before class tomorrow. So what we're going to do is we're going to look at the conjugates of these particular problems. The reason that we use conjugates is based on that factoring shortcut that I taught you earlier called the difference of squares. And the difference of squares eliminates the middle term of a trinomial, and the middle term of my trinomials when I'm dealing with radicals would be the radical values. That's why conjugates work in this particular case. So it's going to be 5 minus the square root of 3. The way that you do this is by keeping the value of the whole number the same. That means it's positive, it stays positive. And you switch the value of the radical from positive to negative, and that's how you're going to get that. So now I can use a difference of squares here. 5 is a, so that means a squared is 25. The square root of 3 is b, so that means the square root of 3 squared is 3, so that's 5 minus 3 equals 22. So that's the way we're going to use that to help us out. If you need to FOIL it, please be my guest and FOIL it out. It's no big deal. You'll still get the same thing. All right, so looking at this, it's the same idea. We're going to look at the value of this staying the same, but the value of the radical, that's the value that must change. So it's negative square roots of 2 minus 9. Now let's go ahead and do double distribution here, or FOIL, so you can see that they're both going to work. So that's going to be negative square root of 4. And then this one's going to be negative 9 square roots of 2. Then this one is going to be a negative and a negative, which is a positive 9 square roots of 2. And then this one, which is positive 81. So now I'm going to go ahead and look at the middle term and see that it cancels. I'm going to simplify this to become negative 2. Negative 2 plus 81 makes 79, and that's how this works. All right, now we built that up to go ahead and rationalize the denominator by using conjugates, like in 13, 14, and 15. So if I'm going to keep the whole number the same and switch the radical, that means I'm going to multiply the top and the bottom of this fraction by 3 minus the square root of 2. I've got to use the distributive property here and multiply that out, and that gives me 15 minus 5 square roots of 2 divided by, I'm going to go ahead and do this one easily using the difference of squares. That's going to be a, so a is 3, so a squared is 9. That's b, so that's going to be minus, the square root of 2 squared is 2. And so now I get 15 minus the square 5 times the square root of 2 divided by 7. That is my simplified form. The only way that I could simplify it anymore is if the number 7, the number 5, and the number 15 all had a greatest common factor. If they do, you can divide that throughout the entire expression, simplifying those 3 whole numbers. The radical or the radicand doesn't matter in that part of the simplification process, so don't worry about that. So the only way that I could have done this is if the 7, for example, was a 3. Then I have a greatest common, or sorry, was a 5. Then I have a greatest common factor of 5, and I can go 1, 1, and 3. Okay? So go ahead and take a look at 14, 15, and as review, 16 and 17, have those ready to go tomorrow at the beginning of class so that we can answer any questions, go over any mistakes, and move on from here.